Welcome to Architecture, All Access Season 4, AI Experiences Unpacked. I'm Darren Crews, and in this episode of Architecture All Access, we will be unpacking AI experiences and the AI PC. I'm a senior principal engineer leading architecture for NPU IP and leading a team of architects focusing on software, firmware, hardware architecture, power and performance, and AI model optimization and research. I've been working on NPU for 7 years and 10 years in the AI and computer vision field. In the last 5 years, AI computing has moved from the peripheries of work and play to a mainstream tool we use every day. In just 2 months, ChatGPT exceeded 100 million users globally. By comparison, it took 4.5 years for 100 million people to join Facebook and around 55 years for 100 million people to fly on a plane. Artificial intelligence plays a major role in society today. But what actually are AI experiences? In this context, we're talking about everything from background blur and noise suppression to AI-generated images, music, and videos. For example, let's imagine that you're working remotely and that you're about to join a Teams call with your colleagues to prepare for an upcoming presentation. Just as you're about to join the call, the idea of using a castle to support the data security section of the presentation comes to mind, but it's too late to get a designer to mock one up. So you open Adobe Firefly and type the prompt, a medieval castle with multi-layer security. Firefly immediately begins creating images based on your prompt, allowing you to join the call while they generate. As you're working close to the beach, you turn on background blur and noise suppression to avoid distracting your team, both of which use AI to run. Even though these might feel like everyday examples, there are several AI technologies at work here, each of which requires a significant amount of computational power. By the way, did any of you notice that the audio, videos, and images used in this last scene were all generated with AI? AI apps can be divided into 2 categories, AI enhanced and AI native. Apps like Teams and Adobe Photoshop have implemented AI into the platform to enhance the user experience. On the other hand, apps like Gigapixel Topaz, which uses AI to upscale image resolution, and Adobe Firefly, which generates images from text, are built entirely around AI. The common denominator for these apps is they all rely on AI models. Features like background blurring and noise suppression use computationally intensive deep learning models that run in real time. Many generative workloads are built on AI models called transformers. Transformers take in any input and use it to generate any output, whether it's video, text, music, you name it. To generate a single image, even the simplest version of Stable Diffusion requires over 800 billion computations. While I don't have time to dive into this here, you can learn more from Tom Peterson's deep dive video. To ensure optimal functionality, the application developers need to optimize the software to point to the feature and its corresponding AI model to the right hardware resources. Underneath our applications and models lies a multi-layer software stack. For any application to execute an AI model, it needs a runtime. These are software environments designed to execute machine learning and AI models by providing the necessary infrastructure, libraries, and tools to deploy AI applications. 2 runtime environments commonly used for AI on PCs are Onyx and OpenVINO. The OS layer is the connective tissue between applications and the hardware, and the key orchestrator for breaking tasks into smaller jobs before scheduling them on the hardware. Below the OS, we find drivers, which are like translators. Imagine a game controller with its various buttons and joysticks. It needs to communicate with a console for the game to work. It does this by the way of a translator, or a driver, which speaks directly to the console. In the case of AI drivers, they translate software jobs into directions on the hardware. At Intel, we use a multi-engine strategy to run AI workloads on the PC, meaning we have multiple engines capable of various AI tasks, the CPU, the GPU, and the NPU. For today's example, we'll focus on the Neural Processing Unit, the NPU. In our example, we're joining a Teams call and had prompted Adobe Firefly to generate a medieval castle. Both the prompt and the model get loaded into the memory via the driver. Then the app tells the driver to run the image generation. The driver will in turn instruct the OS to assign the job to the NPU. Once in the NPU queue, the OS notifies the NPU to start the execution. Halfway through the execution, you joined your Teams call, which activates noise suppression to remove the beach sounds. As a result, Teams will submit a new high-priority AI model. The driver will load the model into the memory, and Teams will talk to the driver, which tells the OS to prioritize the new job. So, the OS tells the NPU microcontroller to stop what it was working on. The microcontroller will pause, save its work on the castle image to memory before confirming with the OS that it's ready for the prioritized task. At this point, the OS will move the new task into the queue and notify the microcontroller that it's ready. You can think of it as the different queues at a passport control. You're waiting at the front of the line for customs to begin checking passports. As you're about to approach the desk, the flight crew arrive, and you're told to wait as they have priority. Once they've been processed, the custom officer begins processing passengers, waving you to approach. In our Teams example, once the job is finished, the microcontroller will notify the OS before passing the finished model to the app. Once activated, the OS will pick up the image generation task while you finish greeting your colleagues, delivering it in time for your presentation. It should also be noted that tasks like noise suppression that deal with real-time situations are refreshed on a rolling basis. In the case of noise suppression, it refreshes every 10 milliseconds to suppress sounds as they arrive, with other tasks, such as image generation, taking place during the downtime. This is a very simplified example of how jobs get scheduled on the NPU. In reality, there's numerous jobs being scheduled simultaneously. To keep the NPU focused on the priority task, the OS has queues of different priority ratings and only feeds those highest priority into the NPU queue. This way, experiences remain fast and snappy throughout the day. Now let's explore the AI engines inside our new Intel Core Ultra processor, codename Lunar Lake. This processor features 3 on-chip AI engines: the CPU, the GPU, and the NPU. The CPU leverages AVX and VNNI to provide robust AI processing capabilities for lightweight, low-latency tasks like background blur. AI on the GPU is mainly driven by Xe Vector Engine and the new Xe Matrix extensions, delivering up to 67 TOPS. Beyond AI in creation and gaming, the GPU is well suited for generative workloads. Our NPU features multiply accumulate MAC arrays, shaved DSPs that are optimized for generative AI workloads. When deployed together, the 3 engines deliver a high-performance platform for the AI PC era. The introduction of this new processor saw some of the biggest improvements to the NPU to date. With Meteor Lake, we introduced the first integrated NPU on a client processor. Lunar Lake takes us a step further with the introduction of NPU 4. We had 3 goals in mind when designing NPU 4. First, drastically increase the compute. Second, improve the architecture for modern AI. Third, improve efficiency for better battery life. We tripled the amount of neural compute engines in the NPU from 2 to 6, resulting in a significant boost in AI inference performance and the ability to run multiple AI tasks in parallel. We also upgraded the shaved DSP, quadrupling the vector performance and bandwidth critical for modern generative AI workloads. Finally, we placed the NPU on the same tile as the GPU and CPU cores, meaning we can use the latest process nodes to deliver a boost in performance and efficiency. With these engines, AI PCs will deliver concurrent AI capabilities across foreground, background, and personal assistant workloads. Artificial intelligence is opening up a whole new world of opportunities, both for our customers and our end users. Intel is committed to constantly evolving and developing our silicon to get the most out of AI and maximize the potential for people across collaboration, creation, productivity, and entertainment. Thank you for joining me today in this episode of Architecture All Access.